So welcome students to this module in which we are going to learn about a very important theorem in econometrics known as Gauss-Markov Theorem. In this module, you will learn about the assumptions under which Gauss-Markov Theorem is satisfied. We would like to prove this theorem and also look at some of the properties of this theorem. We would also prove that how this theorem says that Ols estimators are efficient, consistent and unbiased. We would also look at the goodness of fit and learn about the measures of variation, the coefficient of determination and coefficient of correlation. And in the end, we would take stock of the entire lesson which we would learn in this. Let us therefore understand how this theorem basically moves. You would know by now that using OLS we estimate the parameters B0 and B1 from the sample regression function. However, this estimates of B0 and B1 are from the sample regression function. So we need to make some assumptions about the population regression function so that the sample estimates of B0 and B1 can be used to make inferences about the population estimates beta 0 and beta 1. Now these set of assumptions in econometrics are known as classical linear regression model assumptions or CLRM assumptions. Under these assumptions, the OLS estimators have very good statistical properties. So these assumptions are also known as Gauss-Markov Theorem assumptions. Let us look at these Gauss-Markov assumptions for the classical linear regression models. We have a set of assumptions. So let's begin with assumption number 1 under linear regression model. The regression model is linear in the parameters. This is our assumption number 1. It need not necessarily be linear in the explanatory variables, which means in xi's. Therefore, we can write our linear model as yi is equal to beta 0 plus beta 1 xi plus mu I. Our next assumption, assumption number 2, is that xi, which means the explanatory variables, they are non-stochastic, which means the values taken by the explanatory variables remain unchanged in repeated samples. So the regression analysis is a conditional regression analysis because it is conditional on the given values of xi's. However, within xi's there could be variation. Our third assumption is the assumption of conditional mean of disturbance term, and it should be equal to 0, which means given the value of explanatory variables, the conditional mean of disturbance term is 0, which can be rewritten as, or which can be written as expected value of mu I given xi is equal to 0. Now, if this assumption is violated, then we can show and prove that expected value of yi given xi would not be equal to beta 0 plus beta 1 xi, which is certainly not desirable. This assumption also implies that information which are not captured by explanatory variable or variables and falls into the error term are not related to the explanatory variables and hence do not systematically affect the dependent variable. Next assumption is the assumption of homoscedasticity, and this assumption means that the conditional variance of the disturbance term given the values of the explanatory variables are the same for all the observations, meaning thereby that variance of mu I given xi is equal to sigma square. By definition, variance of mu I given xi is equal to expected value of mu I minus expected value of mu I given xi whole square. Now, since by assumption 3 expected value of mu I given xi is 0, therefore we have variance of mu I given xi equal to expected value of mu I square given xi, and this we are assuming is equal to sigma square for all values of I, which means there is no subscript associated with the variable or with this variance sigma square. Diagrammatically, the concept of homoscedasticity can be drawn and is shown in figure 1 before you, where the variation around the regression line is same for all values of xi. On the contrary, the concept of heteroscedasticity is shown in figure 2, where the conditional variance of the population varies with xi. So you can see in our diagram 1, for every value of xi there is a distribution. This distribution has a mean and a variance. The mean is different for each value of xi because it gives us expected value of the y given xi, which is almost your mean value of yi. But the variance we are assuming that for each value of xi is constant and is same and is equal to sigma square. Whereas in the case of heteroscedasticity, in your diagram 2, you can see that not only the means are different, but even the variances are assumed to be different. So our next assumption is assumption 5, the assumption of no autocorrelation. This assumption basically means that the correlation between any two disturbance terms mu I and mu j, where I is not equal to j, given any two values xi, xj of the explanatory variables are 0. That covariance of mu I, mu j given xi, xj can be written equivalent to expected value of mu I minus expected value of mu I given xi into mu j minus expected value of mu j given xj. This is equal to expected value of mu I given xi into mu j given xj and is equal to 0 by our assumption. Now, our next assumption is assumption 6, which is the assumption of 0 covariance between disturbance term and explanatory variable or variables. And this can be written as expected value of mu I xi is equal to 0, which is same as covariance mu I xi equal to expected value of mu I minus expected value of mu I into xi minus expected value xi, and is equal to expected value of mu I into xi minus expected value xi, since expected value of xi is non-stochastic. Therefore, it can be written as expected value of mu I xi minus expected value xi into expected value mu I. Since expected value mu I is 0, therefore this is equal to 0 by assumption. Hence, we are trying to say that the covariance between mu I and xi is equal to 0. Now, this basically says that the explanatory variables are uncorrelated with the disturbance term. Now, so the values of the explanatory variable has nothing to say about the disturbance term. That is the meaning of this assumption, and it plays a very important role in entire econometric estimation. Next, let us look at another assumption, which is assumption of identification. This is our assumption number 7. Now, to find unique estimates of the normal equations, the number of observations must be greater than the number of parameters to be estimated. Otherwise, it would not be possible to find unique OLS estimates of the parameters, which means that what we are saying is that the number of equations must be greater than or equal to the number of parameters to be estimated. Here, equation means the normal equations which we can estimate by ordinary least square estimation method. Our assumption 8 is that the variance of x must be positive, which means it should be between 0 and infinity. So to find the OLS estimates, there should be some variability in the value of the explanatory variables. In other words, all the values of xi in the same sample cannot be same, which means that sigma xi minus x bar square upon n minus 1 is between 0 and 1. So it's between 0 and infinity. So it has to be greater than 0 and less than infinity. Now, if all the values of xi are same, we would have in that case sigma xi minus x bar square to be equal to 0. Thus, it will not be possible to estimate the OLS parameters or beta 0 and beta 1. Another assumption which we make in our entire Gauss-Markov theorem is assumption 9, which is the disturbance term mu I is assumed to be normally distributed. However, this assumption is required not for estimation but mainly for inference, and it means that mu I is distributed normally, NID normally and independently distributed with mean 0 and variance sigma square, where I is equal to 1 to n. So let me repeat, we are saying mu I is distributed as NID with mean 0 and variance sigma square. So NID stands for normal independently distributed. The normality assumption, as I mentioned earlier, implies that yi is also normally distributed. This assumption is necessary for constructing confidence intervals of beta 0 and beta 1, and hence for conducting hypothesis testing. Another assumption which we make is assumption 10, which is known as the assumption of correct functional form specification. In this assumption, we are saying that the functional form of the regression model needs to be correct, or it should be correctly specified. Otherwise, there will be specification bias or error in the estimation of the regression model. The next assumption is the assumption of multicollinearity, which implies when the regression model has more than one explanatory variables, which means more than one, and we are talking about multiple linear regression model, there should not be any perfect linear relationship between any of these explanatory variables. The above assumption, which is assumption of multicollinearity about the regression model, relates to population regression function. So all these above assumptions which we have enumerated so far are mainly for the population regression function. Now, since we can observe the sample regression function and not the population regression function, we cannot really know if the above assumptions, the assumptions which we have made, are actually valid or not. So let us now state the Gauss-Markov theorem. The Gauss-Markov theorem basically states that under the assumptions of the classical linear model, which are assumptions from 1 to 8, the least square estimators are the minimum variance estimators among the class of unbiased linear estimators. That is, they are blue. Blue means best linear unbiased estimators. And we will prove that. So we need to prove that OLS estimators are unbiased, they are efficient, and they are consistent, especially among the linear estimators. Let us now prove a first property of unbiasedness. So we are going to prove that OLS estimators are linear and unbiased. How do we prove it? Let us see that. The OLS estimator B1 is unbiased if its expected value is equal to population parameter beta 1. So we are saying unbiasedness is defined when a beta 1 has an unbiased estimator in B1. So the estimator B1 is a random variable and takes on different values from sample to sample. However, unbiasedness property implies that on average the value of B1 is equal to the population parameter beta 1. Now we know that the OLS estimates B1 is equal to sigma xi minus x bar into yi minus y bar upon sigma xi minus x bar square. Now this can be opened up and can be in a way written in or rewritten in different forms. So let us multiply the numerator, where we get now sigma xi minus x bar into yi minus y bar into sigma xi minus x bar, and the denominator is as it is, which is sigma xi minus x bar square. Now this gives us to a new term which is sigma xi minus x bar into yi. How do we get this? Because y bar is constant in our numerator in the previous step, and therefore sigma xi minus x bar would be equal to 0. Now from this what we obtain is that B1 is equal to sigma ki yi, where ki is a constant and is equal to sigma xi minus x bar upon sigma xi minus x bar square. Now the ki's has some properties. We can look at these properties, and in fact we can prove all these properties also. For example, you can see the first property is that sigma ki is equal to 0. The second property is that sigma ki square is equal to sigma xi minus x bar square upon sigma xi minus x bar square whole square. Now this therefore gives us equal to sigma 1 upon sigma xi minus x bar square, because in the numerator we have power 1, in the denominator we have power 2, so this cancels out and we get only power 1 in the denominator. The third property is that sigma ki xi is equal to 1, because we in the numerator have sigma xi minus x bar into xi, and in the denominator we have sigma xi minus x bar square. Now the numerator can be rewritten as sigma xi minus x bar into xi minus x bar, and it will be equal to sigma xi minus x bar whole square, which is same as the denominator. So we get the third property as sigma ki xi is equal to 1. So to prove the unbiasedness of the OLS estimator B1, we need to rewrite our estimator in terms of population parameter. So what is B1? B1, as we defined earlier, is equal to sigma ki yi, and let me repeat, I is from 1 to n, which need not be repeated every time. So this is equal to sigma ki, and on substitution of the value of yi, we have beta 0 plus beta 1 xi plus mu I, which is from our population regression function. To open up this product, we get beta 0 into sigma ki plus beta 1 into sigma ki xi plus sigma ki mu I. Now this comes out to be equal to beta 1 plus sigma ki mu I, because we have already proved that sigma ki is equal to 0 in our properties. If you go back, and sigma ki square we have said is 1 upon sigma xi minus x bar square, and we can see from there therefore that sigma ki xi, the third property we had proved, is equal to 1. So what I am trying to say is that we get B0 equal to beta 1 plus sigma ki mu I. Now the OLS estimator is thus a linear function of mu I, and linear because we can see that B0 is equal to beta 1, which is constant, and the second term, which is sigma ki mu I, is linear in mu I. The explanatory variables are assumed to be non-stochastic, so the ki's are also non-stochastic as well, because ki is a function of xi. Now if you take expectation operator on both the sides, we will have expectation of B1 equal to beta 1 plus sigma ki into expectation of mu I, and this is all equal to beta 1 because expected value of mu I we have already proved earlier and assumed is equal to 0. Therefore, Ols estimator B1 is an unbiased linear estimator of beta 1. This was our proof of how B1 is an unbiased estimator of beta 1, and I am sure you all would recollect beta 1 is our slope parameter. Similarly, we can also estimate and prove the unbiasedness of our second parameter, which is beta 0. But we are not giving you that proof here, which is not very essential, but it moves on the similar lines. Let us now prove that Ols estimator is efficient. Now, why are we proving all this? Because once we understand that these parameters have certain properties, we will have more faith and we would understand the usefulness of using Ols estimators. So let us look at this second proof of Ols being efficient. Now, Ols estimator has this desirable property of being an efficient estimator. Now, this efficiency property basically relates to the variance of the estimator. Here we have to prove that the variance of Ols estimator B1 has the smallest variance among all the possible estimators, which means that the variance of B1 is less than variance of any other alternative estimator, say B1 star or any other estimator. To prove this, we have to first define an arbitrary estimator beta 1 hat or beta 1 tilde, which is linear in Y. Now, secondly, we impose restrictions implied by unbiasedness, and lastly, we will show that the variance of arbitrary estimator beta 1 tilde is larger than or at least equal to the variance of Ols estimator B1. So let beta 1 tilde be an arbitrary estimator which is linear in Y. So let us define beta 1 tilde equal to sigma Ci Yi, where I is from 1 to n. Now let us substitute the population regression function in Yi as we did earlier, and what we obtain is that beta 1 tilde is equal to Ci into beta 0 plus beta 1 xi plus mu I. On expansion, we again get in a way beta 1 tilde equal to beta 0 into sigma Ci plus beta 1 into sigma Ci xi plus sigma Ci mu I. For the estimator beta 1 tilde to be unbiased, we need the following restrictions to hold. The first is that sigma Ci from 1 to n is equal to 0 and beta 1 into sigma Ci xi is equal to 1. With this, we find that beta 1 tilde is equal to beta 1 plus sigma Ci mu I. The variance of this arbitrary estimator beta 1 tilde is defined as expected value of beta 1 tilde minus b1 square, which is same as equal to sigma Ci mu I whole square, and is equal to sigma square into sigma Ci square. Now this can be rewritten as sigma square into sigma Ci minus xi minus x bar upon sigma xi minus x bar square plus xi minus x bar upon sigma xi minus x bar square whole square. So what we have done is we have subtracted a term and we have added that term. Now this is equal to sigma square into Ci minus xi minus x bar upon sigma xi minus x bar square whole square plus sigma square into xi minus x bar upon sigma xi minus x bar square whole square plus twice sigma square into sigma Ci minus xi minus x bar upon sigma xi minus x bar square into xi minus x bar upon sigma xi minus x bar square. So students, you must have seen what we have done is in the above equation we had three terms. So we have taken the first two as A and the second as B and then opened the square so that we have A square plus B square plus 2AB. Now it can be shown that the last term in the above equation is 0. So what is the last term? The last term is twice sigma square into sigma, the first term, into the second term. Now this is equal to twice sigma square into sigma Ci minus xi minus x bar upon sigma xi minus x bar square, which is our first term, into minus twice sigma square into sigma Ci into xi minus x bar square upon sigma xi minus x bar square. So we have multiplied both the terms by 2 sigma square. And now therefore what we get is 2 sigma square into 1 minus 2 sigma square into 1, which is equal to 0. This is after imposing the restrictions on the two terms. From this therefore we obtain expected value of beta 1 tilde minus b1 whole square is equal to sigma square into sigma Ci minus Ki square plus expected value of b1 minus beta 1 square, where Ki is equal to xi minus x bar upon sigma xi minus x bar square. Now the first term on the right hand side is always positive except when Ci is equal to Ki for all values of I. Therefore it implies that the left hand side, which is expected value of beta 1 tilde minus b1 whole square, is greater than expected value of b1 minus beta 1 square. Therefore it means that the variance of beta 1 tilde is greater than or at best equal to the variance of b1. That therefore proves that b1, which is an OLS estimator, will have the minimum variance, which means the variance less than or at best equal to the variance of any alternative estimator b1 tilde in our current example. Let us now move on to the proof of the OLS estimator being a consistent estimator. So what is this property of consistency? The property of consistency is a large sample property, or also known as an asymptotic property, unlike the property of unbiasedness, which holds for any sample size. So by consistency we basically mean that as the sample size tends to be infinity, the density function of the estimator collapses to the parameter value. So an OLS estimator B1 is said to be consistent if probability limit of B1 for n tending to be infinity is equal to beta 1. Now where PLM, as we have written in our expression, means probability limit. I am sure you can see that. In other words, B1 converges in probability to beta 1. Now the operator P limit has an invariance property for any continuous function, which means that if, let's say, delta hat is a consistent estimator of delta, and if h delta hat is any continuous function of delta hat, then probability limit of h delta hat for n tending to be infinity would be equal to h delta. Therefore, if delta hat is a consistent estimator of delta, then 1 upon delta hat and ln delta hat are also consistent estimators of 1 upon delta and log or ln delta respectively. Now this property of invariance does not hold valid for the expectation operator E. For instance, if delta hat is an unbiased estimator of delta, then expected value of delta hat is equal to delta. However, this does not mean that 1 upon delta hat is an unbiased estimator of 1 upon delta, which means that expected value of 1 upon delta hat is not necessarily equal to 1 upon expected value of delta hat, which is not equal to 1 upon delta. Now this is because the expectation operator applies only to linear functions of random variables, while probability limit operator is valid for any continuous function. Now we know that B1 is equal to sigma xi minus x bar into yi minus y bar upon sigma xi minus x bar square. Now let us elaborate on this. So this is also equal to sigma xi minus x bar into yi minus y bar into sigma xi minus x bar, as explained to you earlier. And on expansion, you will find, if you substitute the values of yi, what ultimately we obtain is that beta 1 plus sigma xi minus x bar into mu I upon sigma xi minus x bar square. So we have seen that B1 comes out to be equal to beta 1 plus sigma xi minus x bar into mu I upon sigma xi minus x bar square. Now let us take the probability limit and apply the probability limit operator on both the sides. So when we apply this operator on the left hand side, we get probability limit of B1 equal to probability limit of the right hand side, which is beta 1 plus the second expression. Now if you divide in the second expression both the numerator and the denominator by 1 by n, we obtain the probability limit of the first part as beta 1, which because it is constant, and of the second part we have the probability limit of the numerator, which is equal to probability limit 1 upon n into sigma xi minus x bar into mu I, and in the denominator we have probability limit 1 by n into sigma xi minus x bar square. Now these numerator and denominators have been divided by n so that the summation does not goes to infinity when n is, the summation does not go to infinity when n increases and also increases to infinity. So then next we apply the law of large numbers to both numerator and denominator. Now according to the law of large number, under general conditions, the sample moments converge to their corresponding population moments. Therefore probability limit of B1 is equal to beta 1 plus covariance between x and mu, and in the denominator we have variance by x. So which means probability limit of B1 is equal to beta 1 plus covariance x mu upon variance of x. Now this comes out to be equal to beta 1, provided variance of x is not equal to 0. Now we have to understand that covariance of x and mu, or covariance between x and mu, is equal to 0. This we had assumed in our assumptions. So what we are therefore trying to prove here is that Ols estimator is a consistent estimator under the assumptions of the classical linear regression model. Let us, students, after learning all these properties and their proof, move on to the goodness of fit. So let us understand what is goodness of fit and what we have to learn in this. We have estimated our model parameters using OLS and have seen how they have various desirable statistical properties under certain assumptions. But we are still not sure if the estimated model fits the data well, and if all the observations of the sample lie on the regression line. Then we say that the regression model fits the data perfectly, and we can say that the population regression line would be almost equal to the sample regression line. Now usually we will have some negative and some positive residual term, and we want that these residuals around the regression line be as minimum as possible. The coefficient of determination provides a summary measure of how well the sample regression line fits the data. So we have different measures of this. goodness of fit. The first is the measures of variation. Now recall that the sample regression function was defined as yi is equal to b0 plus b1 xi plus ei. Now if you sum both the sides and divide it by the sample size, we obtain y bar equal to b0 plus b1 x bar, which is our equation 2. Now if you subtract this from our first equation, which is our sample regression function, what we obtain is that yi minus y bar is equal to b1 into xi minus x bar plus ei. Now writing this equation, which is third, in the deviation form, we can write down yi is equal to b1 xi plus ei. Now yi and xi are small yi and small xi because we are defining them in the deviation form. So in a way, my small yi is my capital yi minus y bar, and similarly my small xi is equal to xi minus x bar. So my last equation is equal to yi is equal to yi hat plus ei, where yi hat is the estimated value of yi. Now squaring both the sides and taking summation over the sample, we have sigma yi square is equal to sigma yi hat square plus sigma ei square plus twice b1 into sigma yi hat into ei. Now the last term is 0 by assumption that the covariance of the fitted value and the error term is 0. Hence my sigma yi square, which is sigma yi minus y bar square, is equal to sigma y hat minus y bar square plus sigma ei square. So I have replaced my sigma y small yi hat by y capital Y hat minus y bar, and this can be rewritten or can be expressed as total sum of the squares is equal to the explained sum of the squares plus residual sum of the squares. So let me repeat. My left hand side, which is yi minus y bar, is the total sum, and therefore sigma yi minus y bar square is total sum of the squares. My y hat is the explained value, therefore sigma y hat minus y bar square is my explained sum of the squares, and ei is the residual, therefore I have defined sigma ei square as the residual sum of the squares. Now having defined all this, therefore we can say that the total variation of actual y values about their sample mean is equal to the variation of the estimated y values about the sample mean and the unexplained variation of actual y about regression line, which is defined as sigma ei square. So I hope you understand what is total sum of the squares, what is explained sum of the squares, and what is the residual sum of the squares. Therefore, I can say that the total variation in y can be decomposed into two parts. The first part you have seen is explained sum of the squares, which is the part accounted for by x, and the second part, which is RSS or residual sum of the squares, and is also known as unexplained or unaccounted part. And this RSS is known as unexplained part because the residual term ei captures the effect of the variables other than the explanatory variable that are not included in the regression model. Now having understood this, let us now try to understand the coefficient of determination, which is based on this total sum of the squares and explains of sum of the squares. So since we have already defined that TSS is equal to ESS plus RSS, let us now divide both sides by TSS. So we will have 1 is equal to ESS upon TSS plus RSS upon TSS. Now therefore 1 is equal to sigma y hat minus y bar square upon sigma yi minus y bar square plus sigma ei square upon sigma yi minus y bar square. Now we define r square as follows, which is r square is equal to sigma y hat minus y bar square upon sigma yi minus y bar square, which is same as explained sum of the squares upon total sum of the squares. Therefore, R square measures the percentage of the total variation in yi that is explained by the regression model. Now, this would be percentage if you multiply it by 100, otherwise it is the proportion. In other words, therefore, the proportion of the total sum of the squares, which is explained by the sum of the squares or explained sum of the squares, is known as R square. Alternatively, R square can also be defined in another form by little manipulation of the formula. So R square can also be written to be equal to 1 minus sigma ei square upon sigma yi minus y bar square, which is same as 1 minus residual sum of the squares upon total sum of the squares. So R square is now equal to 1 minus the total sum of the square that is not explained by the regression model, and that is what is known as residual sum of the squares. So when the observed points are closer to the estimated regression line, then we say that the data fits the model very well. In such cases, explained sum of the squares will be higher and residual sum of the squares will be smaller. Now we want R square, which is the measure of a goodness of fit, to be very high. So when R square is low, this means there are low or there are lots of variations in y which cannot be explained by x. So high R square is always desirable and is better, and low R square is not desirable. Now there are very many other interpretations for R square. It also measures the correlation between the observed value yi and the predicted value y hat. So it can be rewritten as R y hat. Now therefore R square y hat is nothing but covariance square of yi hat, which is divided by variance of yi hat and variance of y hat. Now this is equal to explained sum of the squares upon total sum of the squares and is equal to R square. So this is by the formula of R square, because R, I am sure you would all recollect, is defined as covariance between the two variables divided by their standard deviations. So squaring the simple correlation between yi and y hat gives the coefficient of determination defined as R square. Now this result is valid for multiple regression model as well, provided the regression model has a constant term. So we can define R square not only for simple regression but also for multiple regression with an intercept term or a constant term. Now the question which commonly arises relates to the value of the goodness of fit. Now there is no rule which suggests that the value of R square is considered as high and what is considered as low, and therefore we cannot pass a judgment that when do we say that the goodness of fit is good or goodness of fit is bad. For time series data, the value of R square is usually high and above 0.9. However, for cross-section data, R square value of 0.06 or 0.7 may also be considered as good. Now we should be cautious not to depend too much on the value of R square. R square is simply one measure of model adequacy. We should be more concerned about the signs of the regression coefficients and whether they conform to economic theory or prior informations. Now the question is, what are the properties of R square? Let us define some of these properties of R square. R square is a non-negative number, and I will show it to you that it will vary between 0 and 1. So it is a unit which is free of both the numerator and the denominator have the same units, so it has no sign. So let me repeat, R square is a non-negative number, R square is a unit which is free of any unit of measurement, R square is a value between R square will take a value between 0 and 1. So when there is a perfect relationship between y and x, we will have residual sum of the squares equal to 0. Hence, total sum of the squares will be equal to explained sum of the squares, and in this situation, r square will be equal to 1. On the contrary, when there is no relationship between y and x, we will have explained sum of the squares as 0 and b1 will be equal to 0. In that case, total sum of the squares will be equal to residual sum of the squares and r square will be equal to 0, which means all the variation in y is left unaccounted by the model and x is not able to explain any variation in y. Now let us try to understand coefficient of correlation. So earlier we have defined coefficient of determination, which is r square. Now we are looking at the coefficient of correlation, which is different from that of goodness of fit. However, they are closely connected. The coefficient of correlation measures the degree of association between two variables. The sample correlation coefficient can be obtained as follows, which is r is equal to sigma xi minus x bar into yi minus y bar upon sigma xi minus x bar square into sigma yi minus y bar square whole under root. So the numerator is the covariance between x and y, and the denominators are the standard deviations of xi and yi. And alternatively, the coefficient of correlation could be obtained also as follows, which is that r is equal to plus minus under root of r square. Now, what are the properties of this coefficient of correlation? The sign of coefficient of correlation can be positive or negative depending upon the sign of the sample covariance between x and y. The coefficient of correlation can lie between -1 and +1, and so we can write that r will be greater than or equal to -1 but less than or equal to +1. The coefficient of correlation is symmetrical in nature. So coefficient of correlation between x and y is equal to the coefficient of correlation between y and x. We can also see that the change in origin and scale of measurement of the variables x and y does not affect the measurement of the coefficient of correlation. Say for example, suppose xi is equal to axi plus c and yi star is equal to db plus d, where a, b and c, d are constants. Then the correlation coefficient between xi star and yi star and the correlation coefficient between yi star and xi star are the same. And also the coefficient correlation between xi star and yi star would be same as between xi and yi. So if xi and yi are statistically independent, then the coefficient of correlation between them is 0. This is another very important property of the coefficient of correlation. However, if the correlation coefficient is 0, this does not necessarily mean that x and y are independent of each other. So the vice versa need not necessarily be true. We also know and we can say that the coefficient of correlation measure on linear association or dependence. The coefficient of correlation measure basically the linear association or dependence. It is not meaningful to describe non-linear relationships. The coefficient of correlation does not imply any cause and effect relationship between variables. This is another important thing which you must try to understand, that it does not give you any cause and effect relationship. The goodness of fit is more meaningful than the coefficient of correlation in the regression context. The goodness of fit measures the proportion of variation independent variable that is caused by the explanatory variable, or it provides up to what extent does the variation in one variable determine the variation in other variable. The coefficient of correlation does not have such significant meaning. So let me repeat, the coefficient of goodness of fit gives you that kind of a cause and effect relationship, whereas the coefficient of correlation does not have any such meaningful kind of a meaning. So students, in this module we have learned first that the classical linear model is based on a set of assumptions known as Gauss-Markov assumptions. The Gauss-Markov assumptions, secondly, we have seen includes assumptions of linearity in parameter, stochastic value of the explanatory variable, expectation of disturbance term to be 0, homoscedasticity of disturbance term, no autocorrelation between error terms, no covariance between error term and disturbance term, identification of equation, variability of explanatory variables, normality of error term, and correct functional form. We have also learned that the assumptions under the classical linear regression model are necessary to prove the Gauss-Markov theorem. The theorem basically states that under these assumptions, the least square estimators obtained by ordinary least square are the minimum variance estimators among the class of unbiased linear estimators. That is, they are blue, means best linear unbiased estimators. We have also learned, students, that the Ols estimator B1 is unbiased if its expected value is equal to population parameter beta 1. The property of unbiasedness implies that on an average the value of B1 is equal to the population parameter beta 1. We have also learned about the efficiency property of estimator, which relates to the concept of smallest variance of the estimator. The variance of OL estimators, they have the smallest variance among all the possible estimators. The property of consistency also has been discussed, and it shows that in a large sample, basically as the sample size tends to infinity, the density function of the estimator collapses to the parameter value. We have also learned that the total variation in Y, which is defined as total sum of the squares, is a sum of two parts: explained sum of the squares, which is part accounted for by X, and the residual sum of the squares, which is unexplained and unaccounted part. The coefficient of determination measures the overall goodness of fit of the regression model. It tells what proportion of the variation in the dependent variable is explained by the explanatory variable. We have learned that the coefficient of determination lies between 0 and 1. The closer it is to 1, the better is the overall goodness of fit. And there is no rule which says that such level of coefficient of determination is high and such level is low. The sign of regression coefficient is very important. The coefficient of correlation, which we have learned, measures the degree of association between two variables, and it lies between -1 to +1. The statistical independence of two variables implies zero correlation coefficient, but not necessarily vice versa. And we have also learned that the coefficient of determination and the correlation coefficient are related with each other, as R is equal to ± √R². Thank you, students.